Okay. Welcome back. We had a good Easter. Weather's turning nice, and it's nice to be outside. We have a couple more things to do. In here, we talk about analysis of variance on today and Friday. Next week is another short week, primarily for some summary, putting things together, and some review. By the end of the week, I should have some study material posted for the final, and we'll talk about that primarily on Monday, and then do more review material on Wednesday for that. And then Friday, there's no class next week, because it's the study day. So homework 10, we're picking up. And 11 will be posted. There will be a homework 11. It'll just be a couple problems on NOVA. It's not going to be a log one. You're also the projects you're working on, but just a couple points to look at within that. And today we're looking at ANOVA, analysis of variance, which is for comparing means in multiple groups, 2 or more groups. We want to understand the data structure, what type of data situations would you apply this to. When are you going to get significant differences between means? What type of signals would you have from graphs and pictures? And then do the implementation on the computer, right, for testing. So we'll do that today, and then Friday we'll look at more, what do you do after you do that testing? Do confidence intervals? How do you do further evaluations? With any questions? The idea of analysis of variance. It's called analysis of variance, but we're really testing about means. Analysis of variance or ANOVA. The idea is that we could have K populations. And then from each of these we get samples. We get K samples. And in the different populations, they have averages. Use of 1, use of 2, use of 3, use of K. You can do this with as few as two groups, right? But you can do it with many more. And in each of these populations, then you get a sample and a sample average in each of these 2 things, each of these groups. So Y bar 1 is the average in group 1 data, and Y bar 2 is the average of the group 2 data, etc. And the question basic question we're going to ask, right, so are these averages the same? That's going to be our null hypothesis. Or different somehow. Is there some difference? So we want to look at all the data together to come up with an overall statement. Is there any difference or not? A follow-on effort then would be, how are they different? Which pairs of means are different, or a group of means different from another group, and so on. But first we want to establish that there's a difference or not. So there's a model, a probability model that underlies these methods. That we have groups and individuals. We get 2 subscripts on this. So the model, right, says this is the measurement. It's I or J. So measurement in group I, subject J. This is the average, theoretical population average in group I. And this is some random deviation. For group I for a particular subject. So let's say that the individuals are clustered about their group averages with some variability about that. So a picture you could get out of this, the other assumption that we made is that these errors are independent, normally distributed with some constant standard deviation. But the model, the probability model for how our data are supposed to look, could look like this. Like here's the distribution for one group, here's another group, and maybe a third group's over here. So maybe this is mu sub 1, and under that center is mu sub 2, and under this one, this heap over here is mu sub 3. So if we had 3 groups, maybe their averages would be spread out like that. And our actual measurements for the groups, say for this first group, say mu sub 1 here. Right, if we actually get data points here, we're going to get some values around here. Maybe our x's from the first group end up being there. Mu sub 2 will give us something, so those in green. If the second average is here, right, I'll try to draw them. I'll draw them a little bit below so you can kind of see the difference. They're going to overlap, some with this other group, but they're kind of shifted a little bit. And if we get data from a third group, well, it's going to be kind of over here around this one. Right? And I'll just draw it a little bit above the line so it kind of sticks out. So maybe our data points would be here. That group would kind of stick out a little bit more. But they're going to get some x bar 1. Oops, x bar 1 is the summary of this one. 3, right? X bar 3 for the third group. Going back to my colors. The second one is over here. X bar 1 would be somewhere in here. X bar 3 would be somewhere in here. And then the X bar 2, kind of maybe it's pulled up here a little bit away. The X bars will be a little bit away from their averages. But we have these 3 different groups, and we want to decide, is there enough spread in these X bars, accounting somehow for the variability in the measurements that might overlap, to say that we're sure that mu1, mu2, or mu3, that there's some difference there. Right? In this little picture, maybe you can't distinguish these two because they overlap too much, but maybe that one sticks out. You could have all 3 different, you could have 2 overlapping and 1 sticking out. Right? Once you get 4 or 5 groups, you can have all sorts of patterns. You can have 2 up here and 3 down here, right? And that would be a difference. Or they could be all 5 different. And so analysis of variance is about testing that. And to go about that testing, we're going to think about deviation. So we have Yij. We have a certain number of groups in our data. We have some individuals. So in sub I, individuals in group I. Now I'm going to show you some formulas, for this to kind of set things up briefly. Mostly we'll take things from the computer, but I want to show you a few formulas to show you where some of the things come from. So we can calculate the average in a particular group just as a sample average. Writing it like a sum, J is going to go from 1 up to n sub I of these individual things. So this is the average, sample average in group I. We can also have kind of an overall average. 1 over n, we can sum over all the y sub ij's. If you wanted to write it mathematically, one way of writing this thing is you can actually have a double sum. Of the yij's. So what this ends up meaning is that you take all of the y values that are indexed by their group and which person they are in that group, you add them all up and divide by the total number. And it's going to be the sum of all of our observations, total sample size. Now, total variation. What's the total spread in all our y values? Right, so total variation is relating the the individuals to this overall mean across all the groups. Right.
Oh, you go back for a second.
Yeah. Right. Anyway, these are the symbols for it. You'll see them in the book. They're related to the things that we're going to do.
What's that Y with the
Double bar. This is the overall sample average. Yes.
Under the second summation, is that J equals 1?
Yeah, this is
Okay.
J. Second index J. There's analysis of variance. We're going to talk about one-way analysis of variance where we have one dimension of the group. So once you get 2 dimensions or 3 dimensions defining the groups, like you might in an agricultural experiment, right? You might have different chemicals, different genetic seeds, different planting schedules. All those things can be thought of as different factors that would define different ways of doing things. So then things kind of get crazy. You might have 3, 4 summations and to write out the algebra of all this, right? That's the overall sample, averages in the groups, and individuals. Right? So kind of 3 levels of things there. Sure. Yeah, it's a lot of notation. The idea is that this is overall average, averages within groups, and then variability of individuals around their individual groups. The total variation. How does an individual differ from the global, the overall mean? Right? That can actually be broken into 2 pieces. Right? This thing is equal to Yij minus the group average plus the group average minus the overall average. This one is essentially like between groups. And this is really the difference within a group. How does an individual differ from the average in its particular group I, right? And this is how the groups, how are they different from the global, right? So you can kind of break it into, here is the overall, the groups are slightly different from that. And then within a group, the individuals are slightly different from their averages. So it turns out if you square this thing and add over all the subjects, you get something called sum of squares. So this is at the basis of what's called this sum of squares relationship. So the sum of squares relationship, if you add over all the individuals, and I'm just going to write a general sum. We're not going to mess with writing all the individual double summation indices. We're going to try to go for the big picture. This one is called sum of squares total. Sum of squares. And it ends up being decomposed into 2 parts. There's a sum of squares error, or sum of squares within the groups. How do the individuals differ from their averages within each group? It would be a sum over the Yij minus Y bar I squares. Sum of squares error. And then there's a sum of the Y bar i's minus the overall. There's a sum of squares due to the group. But our total variability breaks into one is how are the groups different from each other, and then how much variability is there within each group. these things, along with a little bit of extra, gets put in what's called an analysis variance table. Total variability or uncertainty is broken up into these four pieces, and they add up. Little math, little cross products, little expanding the squares and stuff. Something cancel, the cross product cancels, so it ends up being these two things added together, which is kind of nice. So the way this gets put together is in something called a ANOVA table. And R, or any statistical package, will compute this for you. So there's a source of variability. And right now we're looking at the groups or error and total. And there's this sum of squares column. There's a sum of squares total, a sum of squares error, and there's the sum of squares due to groups. And they add up. Right? If the groups are really different, right, sum of squares group is big. Right? On the other hand, if the groups are kind of the same, but sum of squares error is most of the variability, right? It's just high variance in a group. Right? Then more of the variability will be in the sum of squares error. Right? But if the groups are really different, you're going to get a fairly big chunk of the total divided up into this group part. Right? Associated with each of these is a degree of freedom. We're going to calculate something like a variance, right? In our ordinary variance, sample variance formula, we have 1 over n minus 1 times the sum of the square deviation. Well, this thing in the notation is kind of like this one. Right? Degrees of freedom, or df. Overall, it's n minus 1, just like it was when we had one sample. Right? For groups, if there's I groups, there's I minus 1 degrees of freedom there. So if I averages, there has to be a global average. So there's I of them. I minus 1 separate deviations from some average. Right? And for error, there's n minus I. And those things add up. Right? So there's n subjects, I groups. Right? So you have n pieces of information. We're estimating I things, and so that's what ends up being. That's the next column that's in there. And then the next column is called mean square. It's basically doing this thing, right? Taking the sum of squared deviations divided by degrees of freedom. Right? So the mean square for group is called the sum of squares group divided by its degrees of freedom. And the mean square error. Sum of squared error divided by its degree of freedom. You could calculate the mean square total. We usually don't. It's not relevant in future calculations, and those things don't add up. So usually, tables will just show you these two things. Now, if the groups are really different, sum of squares group is big, and consequently, the mean square group is big. If, on the other hand, groups are kind of the same, and this thing is pretty small, most of the sum of squares is in the error component, is the variability of the measurements, and the mean square error will be larger. So if there's a big difference in the groups, we expect this thing to get bigger than that. And so the F statistic for testing whether there's a difference in means is this mean square for groups over mean square error. So you get the sum of squares total from how the y measurements vary about their means, and the degrees of freedom, you calculate, divide, you get the mean square errors, and then take the ratio of those two things, and you get an F statistic, right? And under that normal model, this F statistic has something called an F distribution. There's a probability distribution for it, right? If that F statistic is big enough, it's hard to believe that the means are the same, right? If the means are quite different, and this is big, and the mean square is big, and the F statistic is big, it's pretty implausible that they're really coming from the same population. So, so we use this in testing a null hypothesis. The null hypothesis states that they're all the same. Same average or expected value or mean. And the alternative is that some use of J is different. I guess I call it use of I. Is different. So and that's just very general. It just could be one of them is standing out as different. There could be two, or separated in any different pattern that is not all the same. Under this assumption, under H0, our F statistic is a random variable, random probability distribution. With what's called an F distribution. And it has degrees of freedom. It actually has 2 degrees of freedom, one for the numerator and one for the denominator, because it's a ratio. With an F distribution. F distributions are positive. They look kind of like this. So that's my picture of an F. And if all the x bars are exactly the same, and there's no sum of squares group, there's no difference between means, we're at 0. This would be, we're down here, all x bar i's, y bar zetas. Are about the same. On the other hand, for up here, right, the mean squares for the groups has to be large relative to the standard errors. So if we get far enough out there in the F, we're going to reject the null hypothesis. And if we get out here, if this is a 2 or 5% area, in this area, far enough out, we reject the null hypothesis and conclude that the means must be different. So there's a lot of things that are analogous to what we did in other testing. We have a model, we set up a statistic, we figure it out for some transformation of that statistic, whether it's normal or T or now F or chi-squared, right? That a certain size of that statistic, very big values in this case, mean that the null hypothesis is unreasonable. It just does not work with it. And we actually have a probability distribution that comes out of this that gives us a specific cutoff, and if we're far enough out, we can reject it. And the 0.05 is our error rate. If there's really nothing going on, we only expect to be out there 5%. So we're going to live with that possible 5% error rate so that we can reject something. That's kind of the core of analysis of variance, right? It brings together all the groups and all the data so that we can test. Does everybody have a copy of the handout? Right, so we're going to look at some data. The data that we'll look at today is a few times in the book. Professor Rosner has looked at some lead data. These are testing children who lived near a lead smelter, 1972, 1973. And there were 3 groups in there. So the data set, here's the Excel form of a data set. There's actually, so we go all the way back to here, an ID, which area they lived in, the age of the children, male, female, then some IQ components, right, and then some other, what lead group were they in, what was their blood lead measurement values in 1972, 1973. The area has to do with whether they lived near, how close they lived near to a lead smelter. I mean, lead's used for things. There's places that make lead, right? And so some people live more or less close to those. And as described in this book, was this within a quarter mile or within a half mile or a mile, or more than a mile away from this lead smelter. And lead is toxic. It affects neurological system. That's why it's not used in gasoline or paint anymore. Right? And this, back at that time, there was measurements of, some of these things. Do they have convulsions? Do they have irritability? Do they have clumsiness? Do they have colic? They recorded the total years they were living near that smelter, right, in that area. They have other auditorial, they have finger, wrist tapping things, so dexterity measurements for children with their hands and fingers, right? How can they do this? If they have interruption of the neurological cycle, then they have problems with that. And so on. So a bunch of different variables are in there. If you read it in, there's a version stored as a R data set, so that one's read in. These are all the names of the variables that are on there. To make it easy to refer to those variables, I'm going to use this attach command. I already did that. There's a lead group depending on exposures. There were 78 in the first group, 24 and 22. These are based on groups based on how much lead was in their blood, right? And here's the first group. This is a box plot of the lead in 1972, right? And so basically, group 1 is less, and 2 and 3 are higher. If you look at the 1973 measurements, the group 2 is higher. So I think group 2 is defined by high lead concentrations in both years. 1 is low in both years, and 3 is kind of in the middle, right, for that. So what we want to do is, based on those groups, those kind of observational groups by how much lead exposure there was, look at an outcome, right? So the maximum finger wrist tapping exercise, I'm not quite sure how you do it, right? But they get a score. And here's a box plot of the different groups, measurements within the group. Right? So if you're making box plots, you can put labels on this. You can put a Y label as finger wrist max, and put that max finger wrist tap onto there. And maybe an X label equals lead groups. Right? If I do that, I don't think I need that. Oops. Let's see. What do I need? I needed a box plot. Label, oops, there's an extra, that's what the problem is. Okay, I think that'll work now, right? So I can put my lead groups here and make it look a little bit nicer. So do you think, in terms of this max finger wrist tapping, there's much of a difference between these 3 groups? Here's the medians, right? 2 is a little bit lower. 2 had the most lead exposure. Its scores seem to be a little bit lower, but they overlap a lot. Right? Mediums are not. Maybe the averages would be so different. These are, there's a kind of a convenient way here to split it. If I took the mean of max FWT and I could lead group, I can say that, does that one equal 1? Right? The mean is 62, the mean equals 2, group is 3. So I can just calculate those three averages there. Now for a project, right, if you had data like this with 3 groups, you could take just one group and do a confidence interval for a mean. Right? Or if you took two of the groups, you could do a hypothesis test or a confidence interval just for comparing two groups. Right? You get the mean, standard deviations. You either can do it in R, or you could do those calculations for one or two samples just by the formulas and putting in the numbers you get out from summary. Right? And that'd be two statistical procedures related to this. Right? You could also get three groups. You could do ANOVA as well. You could make a description of a box plot, a description of the averages. That could be your descriptive section for things, right? So is there a difference, right? In R, there's a LM, a linear model command. This is actually an example of a linear model. Y is related to the averages directly. So LM does it, and this R command, the first thing there is the outcome. That's our Y variable. And there's a little tilde here. Distributed as or a function of, and we want lead group. Now lead group is coded as 1, 2, 3. So if you put 1, 2, 3 in there, it thinks it's quantitative and tries to do a slope. 1, 2, 3. We don't really want that. We want separate averages. So telling it to treat it like a factor means that it will treat it as three groups, right? And so analysis ANOVA gives us this output from that. Right? So in this output that you have there, so if I do this, right, it gives this output. Right? It's named things a little bit differently, but it's the same format, right? Certainly you see the columns, degrees of freedom, sum of the square, mean square, F. That is actually a p-value. The probability you're bigger than the observed value. Right? And it gives you the variable name here for the thing defining your groups. Right? It doesn't say groups or model or something like that. It just gives you the name, which is nice in a way. It doesn't call it error. It calls it residuals. Right? Error is residuals. Yeah. If you go to a different computer package, different book, they'll name it slightly differently. They're kind of used interchangeably. Right? So in terms of this table, right, what you would get out of this, let's put degrees of freedom. Let's do it in their order. Right, so the groups, which are defined by lead levels in here, degrees of freedom, there's two of them. So 3 minus 1 is 2. Error or residual. It might even say individuals, right, because they're subjects. In this, there were, what does it say? Where's my, no, there it is. It says 121, so there was 124 subjects minus 3 is our 121. Total, it doesn't give you the total. The total would be the 124 minus 1, or 123, and these things would add up. It calculates sum of squares for you. Sum of squares groups is 1136. Sum of squares error is big, 59185. And the total, if you added those together, would be 1, 11, 12, 2, 3, 60. If I read it right. That would be the total sum of squares. So the R output is the mid there. The mean square, or MS, right, is you just divide. So 1136 over 2 would be 568, 0.01 if you have their extra decimal place there. This one is a 59185. So that the sum of squares often looks really huge, right? But you divide it by the larger, something related to the sample size, right? So divided by 121. And it comes down to 489.13. Our F statistic is the ratio of those two things, so 568 over 489 comes to be about 1.16. That's the statistic. Is that large? Is that small? We're going to compare that to an F distribution with these 2 and 121 degrees of freedom. Right? So the 2 and 121 come from the numerator and denominator in there. And you can calculate that the probability that this F distribution would be greater than or equal to our actual number is that p-value there, 0.3166. The thing that's out here is their little notation, p-value, 3166. The probability that you're greater than an F. And p-values that are bigger than 0.05 right, are not so surprising. Right? They're not small. Right? So in this case, we can't reject. So do not reject. Null hypothesis. The null hypothesis, right, is that the average maximum finger wrist tap score is the same for all three lead groups. We can't reject that. Right? The groups looked quite similar. You know, statistically, we can't say that they're significantly different. If it was significant, well, maybe then that the lead exposure is causing that group to have a lower score. But on this measure, we can't say that. That's not significant because the averages weren't different enough. The sum of squares for groups wasn't big enough because the groups weren't so different relative to that error. Right? You go through the F statistic. So if you do a picture related to that F distribution, right, the F would probably look something like this. And then we must be something about here, 1.16 or something. And there's 31% above, 32%, 1.6. Let's get all of it. Right. So we're kind of in the middle. It's not surprising. So we're looking at variability and spread, but really answering something about the averages. Right? But any questions about what things? So primarily, on an exam, I might give you a table like that, right? And then give you a picture and say, do you see any difference in groups? Look at the ANOVA output. Is it statistically significant? Right? Look at things like that. Now the F table, because it has 2 degrees of freedom, takes up about 6 pages in the book, so I probably won't copy that for you. Right? There's an F function in R. Right? So if you ever needed to, you can get probabilities associated with an F distribution. You can give the density. It has a density. I don't know. There's a function that related to computing the probabilities related to it. And of course, like 251 probability, which I'm teaching this spring, we kind of go through the things to get up to that point of seeing where the F distribution comes from and transformations. This F distribution gets used more in next level courses in statistics that would do things with multiple regression and so on. But we can get the probability that you're less than a certain value, 1.16. You put the degrees of freedom in there, 2 and 121, about that. And so the probability you're greater than that is 1 minus. And that's where the p-value comes from. Right. Another thing that comes out of this is an estimate of sigma. Right? So the model says that the Yij was the group average plus this an error term, and the errors were supposed to be normal, mean, 0, and standard deviation sigma. We can get an estimate of sigma squared, the mean square error is an estimate of that, and so our estimate of just sigma, the standard deviation. Now that standard deviation has the same interpretation as a standard deviation in just a single normal. Right? We have one group, there's a mean plus or minus a couple of standard deviations, is usually the range of the data. Right, so the estimate of this is just the square root of mean square error. Some computer programs call this the root mean square error in that. And so in this ANOVA output here, the mean square error in this case was 489.13. And so the estimate of sigma is 489.13, which I don't remember what that is. So the square root of 489.13, square root of 489.13, about 22.1. Right? So here's this mean square error. That's the number that I'm getting in there. So the estimate of sigma in that model is 22.1. So that's variability in the risk tapping scores within groups. So let's look at, so do you think anything, we're looking at some other outcomes. Let's go back just a bit. What's the plots here? Right. So these are the box plots. You think about kind of the center plus or minus 22, plus or minus 44. Right, if you take something near, like an average near the middle, plus or minus 20, plus or minus another 20, right, it kind of goes most of the distance here. This one, yeah, there's a couple outliers and a little shorter, but still, for the third one, you take the average, plus a couple standard couples of the sigmas, sigma hats, right, you get plus or minus 22. It goes, well, it tells you kind of the range of the spread there. Generally you want, so the standard deviations within groups, these are the standard deviations. And our pooled one from that root mean square error is about 22. So it's kind of in between those. When we do the two sample t-test, I said I like it when you pool them. I mean, this is the analogy. That's kind of the standard thing that people would do in ANOVA is pool it. So this one's kind of a between the groups. So you get a little bit of extra information from the table. How about other outcomes? IQ verbal, IQ something or other, and then this other IQ. Right? These things don't look like there's a whole lot of difference there. Right? A little subtle difference in medians, but right? Not a whole lot of difference there. It's hard to see much. Right? If you run the ANOVA for this, degrees of freedom look like they're the same in there. Now for this one, this is IQV. IQV, right? This even had a smaller sum of squares than the other one. Right? And so the F value is even smaller, and it's not significant in there. Now if you go to the IQF, it had a slightly bigger sum of squares. Its p-value wasn't quite as small. It's still hard to see. Well, that's IQP, IQ, where is it? IQV, right? So there's still, maybe there's a little bit of a slight difference, but it's pretty small, right? And this last one is IQP. Now this one, somehow, IQP, this plot, I mean, the medians look quite dissimilar, right? But if you look at the average differences, the first one ends up having an average of 102, whereas these others are 95, 94. Kind of the first group, it's hard to see from the box plot, but the first group looks, because of these outliers, probably the average is pulled up a little bit. And this one looks a little bit skewed going down, so the average is pulled down. And this suggests that that's enough for them to be significantly different. Now the box plots don't really show it, right? But if you do this test, it is, the sum of squares get bigger, the averages are more spread out on this square, on the scale. Everything, if you get a different variable on a different scale, like if you go from, if this was time, you went from seconds to minutes to hours. Of course, the scale of everything here is going to change. The F value is still on the F scale. It doesn't have any units. The ratio kind of wipes it out. But it gets a p-value that's 0.03. Right? The F value is 3.61 on these degrees of freedom, and that's a little bit big enough. Another way this could be, you could look at the quantiles. How big would that F value have to be for us to reject? Well, that's a quantile. The upper 95th quantile or percentile of an F with 2 and 121 degrees of freedom is 3.07. Right? So we had to get this F ratio being 3.07 or more to reject at the 5% level. Right? And we got past that. Right? So that one shows up as significant. And the 2 and 3 groups that had higher lead exposure are lower in terms of that IQ score. It would probably be more convincing if several different measures showed, related neurological function, showed a deficit in these lead groups. But, something does. Right. The next thing is really to look at, we'll talk about this on Friday, but once you get something as significant, you often then look to see if there's differences between pairs. Is the first group different from the second? Is the first different from the third? Is the second different from the third? Or maybe the first is different from the average of the other two. It's called a contrast, right? That would be the next investigation, and that's part of this. Other things, clumsiness, irritability, convulsions, hyperactivity also didn't really show up, right, as significant in this particular study, right? So, yeah, that's kind of does this mean that lead exposure is not related to these things? Maybe it's, if this was the only study that was out there, right? One thing to keep in mind is how many subjects were in this sample? I mean, it's like 24 or 28 in the two small groups. It's pretty small, right? There's a lot of things that go into IQ measurements or dexterity measurements. Are the children being taught at home? Other genetic considerations, social considerations. It's possible that all of these individuals had higher blood lead levels than somebody that would live out in the countryside away from the concentration of the pollutants. Right? So if these groups weren't that different to begin with, right, it's not really saying that if you eliminated the excess lead exposure, there wouldn't be a difference. This study is one that is kind of an example of one that's probably underpowered to detect differences, right, because it has small sample sizes. These type of differences in scores, particularly for some of those, like these differences in averages, if you had a couple hundred in each group, might very well be significantly different, and kind of overwhelmingly so, if they persisted right through that. But anyway, that's probably enough technical stuff and enough computing for right now. The one thing to kind of say, to kind of come up is like, this can be used in a lot of different circumstances, right? So, how are groups formed? Right, so this one, the lead exposure groups. They're really observational. Right, because it just occurred in nature. We're not randomizing people to exposure. And there's some choices, right? There's some cutoffs, right? They chose levels of lead in 1972, 1973, and formed 3 groups, right? These are really, in this case, they're derived from strongly quantitative. Measurement, like cutting these 72 and 73 leads into low and high. You could do other analyses, right? If you have quantitative lead exposure, or maybe cumulative duration of lead exposure, some in a smoking cessation literature, they talk about pack years. How many years, packs of cigarettes for a year have somebody smoked during their lifetime? So if somebody smoked a pack a day for, for 10 years, right, you have that cumulative exposure. Maybe there's a cumulative exposure to lead too. So you could use this to get a quantitative measure and do that. So you might do regression instead of groups. Groups is still interesting. Right? Another big way that you might get these are observational, other types of other categorical, observational data. Right? You could compare into women, you can compare race, ethnicity, you can compare people, students by first, second, third, fourth year student, right? And you can compare people by geography, they live in the Northeast, urban versus rural, urban, suburban, rural. There's actually several different levels of ruralness depending on the county you live on. Right? Another big way you would get groups is randomized experiments. So you could have, treatment and control. That could also be methods for two groups. But you might have treatment 1, treatment 2, or control. Okay? And be comparing things in the diabetes prevention program. There's metformin as a drug and a lifestyle intervention versus placebo. Kind of giving basic information about health. Right? And so you can get these multiple groups through a randomized experiment. And then you're looking at are the differences caused by the fact that people got different exposures, right? So ANOVA would be a first-line thing for, a lot of different types of analyses that are there. Okay, so on Friday we'll come back. We'll look at a couple more applied examples, a couple more things to interpret with ANOVA. It'll be another chance to look at the output, good preparation for doing the assignment that will be coming out of it. And if this is relevant to anything you're doing for a possible project, there'll be more examples of interpreting the algorithm and summary. If you have homework 10, go ahead and drop that off. You could bring it Friday. You can always send it to Friday if you want to get that done. So.
Sorry.
No, that's all
I
right.
don't know where my head was.
Well-
I was so focused on an Orgo exam that I kind of just put everything else out.
I mean, a couple students have said, they have another, like a final thing to do, like a final paper or something. A couple other students have asked for extension until the Friday, and there's nothing really wrong with that. We're just kind of moving on. There'll be something else,
Yeah.
coming down there, but so Friday's fine.
Okay, sorry.
Yeah.
Thank you.